Hi, thank you for tuning into this demo. My name is Hanny Dow, and I'm a senior applications engineer with Multilane. And right now, I'm going to be talking to you guys about ThunderBERT. ThunderBERT is our brand new flagship bit error rate testing software for all of our primary BERTs. Now, we brought this software out of the need to really change the game when it comes to high-speed layer 1 testing. 200 gig, 400 gig, 800 gig technologies, they've introduced new considerations and new rules and new methods to test and optimize devices that need to be fully certified before being deployed into the market. New considerations like advanced equalization techniques, error behavior, PAM4 modulation, and forward error correction tracking, introduce new rules for what it means to be able to bring these devices out there. One good example is like a 400 gig transceiver, which I'm holding right here. This 400 gig transceiver runs on PAM4 modulation. And the interesting thing about PAM4 devices is that they are no longer expected to run error-free, which means you need to be able to have a comprehensive understanding of the error behavior. You need to be able to understand what equalization techniques lead to optimized performance. And finally, you need to understand how your device will respond to forward error correction, encoding, analysis. We have all of that and more that we're going to introduce in ThunderBERT today. And what I'll start with is on the left, you will see our hardware setup. This is our 4039E, our 4x58 gigabaud BERT, which once you account the PAM4 is a full 400 gig BERT, which is available today. And we're going to have that BERT just in a direct loopback, transmitter to receiver, so we can show you the new software features. So you'll see our ThunderBERT icon is over here on the right. I punched in my static IP of this device, and I will press connect. And the first thing you'll notice is that just about immediately, we are already in the BERT window. So we call it ThunderBERT because we think that's a great indicator of how fast this new version of our GUI is. You will notice that everything is super responsive. And when we really want to talk about speed, let's say change our bit rate. Okay, right now I'm at 53.125 gig. That is the nominal baud rate for 100 gigabit per electrical lane. But I'll go to a lower baud rate, like 26 gigabaud. I'll press apply, and you'll see in less than a second, all of my receivers and transmitters configured over to 26 gigabaud, and everything is locked almost instantly. And I will do the same with my modulation type. Let's switch from PAM4 to NRZ. Okay, I just switch from PAM4 to NRZ, and you'll see some locks flicker for a few seconds, and just like that, we are back in action. So I'm going to go back to 53.125. That's where we're going to be testing at today. And then I'm going to switch back to PAM4. And again, super quick, super responsive. We're back in the condition we want to be in. So let's start by introducing what we can offer for configuration in the transmit and receive menus. So we operate the transmitter in 3 separate modes, whether it's optimal mode. Optimal mode allows you to just set a target calibrated output amplitude, or in 2 different advanced modes in which we introduce a 3 or 7 tap transmit equalizer, which will really allow you guys to have very precise control over the output shape of the signal. This is hugely important, and we're going to talk about it in further detail in a few minutes. But for now, you'll see, I have that 7 tap mode in which I can very finely tune the output shape of my signal with such granularity that I can even set a certain target loss out of my signal with our channel emulation feature. So if I enable channel emulation, I can go ahead and just punch in whatever loss I want at the Nyquist frequency. That will be around 26 gigahertz. And I can sort of set that in, and my taps will change to ensure that I have now 5 dB loss in my channel. I'm not going to really put that much focus on channel emulation today. I just wanted to really introduce that feature to you. We have very fine controllability of the output of the signal, whether to optimize it or to, let's say, make it a bit more strenuous to determine your DUT's responsivity to a suboptimal output signal. And that's really the key test that a lot of folks have been interested in these days. So let's go back to 3-tap mode for now. Another thing you'll notice in the transmit window is I can set the TX pattern. So we have a bunch of PRBS patterns, pseudo-random bit sequences to select from. I can select PRBS 7, and you'll see my receiver, which is expecting PRBS 31, loses lock. I will go back to PRBS 31, that's PRBS 31Q, for PAM4, and my lock is restored. I can do the same thing by disabling the transmitter. You'll see that lock is gone, that lock sign is now red. I'll turn it back on, and almost instantly our lock is back on. So on the receiver side, I can also change that pattern, and I can also do something called an RX inversion, which flips the polarity of the incoming electrical signal. However, since my polarity is correct in the hardware setup, I'm just going to keep polarity normal to ensure the lock stays. If I pop into the RX Diagnostics tab, you will see I have the ability to track the histogram, the logical sort of depiction of the 4 levels of the PAM4 signal, just like that, of all four signals. And I can also show the real-time signal-to-noise ratio of all 4 channels. Right now, all 4 channels are running at around 24, 25 dB. That's an important number we're going to come back to in a second. Another component is the RX side equalization. Now, by default, we implement a 15-tap FFE equalization implementation on the receiver side because that is very representative of what your DUT, like an optic, will be subjected to in the network environment. So we have that FFE tap as equalization running, but you also have the option to set your DFE, decision feedback equalizer, to set your reflection canceller, level dependent equalizer, or your multipath interference canceller on the receiver side. And we're going to leave that alone for now. We just wanted to show you that our equalization options are very, very comprehensive on this BERT. So I'm going to go ahead and kickstart a bit error rate test. To start a bit error rate test on ThunderBERT, I select my x-axis. I'll go with time as my x-axis, and then I will select real time and instant BER. And then I will go ahead and make sure I'm running a continuous test, and I will select the 4 channels to all run simultaneously. So I get that started, and okay, you can see the graph updating, but you don't really see any activity on the graph right now. That's because right now I have configured the taps in an optimized setup to run error-free. And now I stop the test, and I will pop open the details tab to show you now you have all the measurements being depicted in real time. Regardless of whatever you put on the graph, whenever you start a test, all of the measurements are going to be available for you to see in both real time and instantaneous implementations. And let's say I only care about real time BER. So I can go ahead and just select real time BER from the filter tab. And now you see real time BER, and you see that they were all running around error free. And now we come back to the conversation of the equalizer. We come back to the conversation of optimizing signals for these DUTs. It's all about the trade-off between bit error rate performance on one side and power consumption on the other side. We have 400 gig electrical channels running error-free right now, but that's not very realistic of the type of electrical signal which is going to be fed into this DUT. So what I'm going to do is I'm going to load a pre-configured setting where I actually have a higher bit error rate coming out of these transmitters. So I'm going to go ahead and select a configuration where each of my transmitters is going at around 1e-6 of a bit error rate, and that is a bit more representative of what a device like this would face in the real time network environment. It's a bit higher than what I would expect out of a 400 gig switch, but for the purpose of this demo, we wanted to show you that we could use our multi-tap equalizer to configure that output bit error rate to be really whatever we want it to be. So now that we have some errors coming in, let's run that test once more. And something I'll actually show you is now that we have degraded those output signals a bit, I can select all 4 of the SNR metrics to show that we're running now at 20 dB instead of a 25 dB, which we were running with the optimized signal. So that's an indicator that the signal has been degraded. So without further ado, I will go ahead and I will start. This time I'll add a bunch of measurements on the graph side so you can see the advanced graphing capabilities of ThunderBERT. So I have real-time BR, instant BR, and instant and accumulated error counts as well. So I'm going to go ahead and press start, and now you can see a lot of activities happening. I'm going to go ahead into the details tab, and this time I'm only going to show time, real time, and instant BR. And let's say I only show just channel 1 to focus on one guy, so that I can simplify really my real-time readout. I turn off the filter tab, and you can see channels 2 to 4 are minimized, but we still have all measurements coming in. I can stop measurements on the graph, but that will not really change the fact that the measurements are still being tracked in the details tab. So whatever I show on the graph is completely independent from the fact that I'm tracking all the measurements at once. So let's say you started this test in your own lab, and then, okay, you see 4 channels running 1E-6. That's what you expect. Let's say you get pulled into a meeting. Let's talk about error bursts for a second. Let's actually implement an error burst with our error insertion feature. So I'm going to go ahead and insert a bunch of errors on the LSB side of the output pattern. So I'm just going to do that for a couple of seconds. And now you can see, if I hide the details tab for a second, that channel 1 now shows a huge jump in the real-time and instant BR. So that is representative of, let's say, an error burst, which could potentially break your link in the field. So you need to be extra careful to be able to identify and get to the bottom of those error bursts. Now, what we do to enable you to have full visibility into the error profile of your device under test is a feature we call history navigation. So I went ahead and I enabled history navigation in the details tab here. And now I have a cursor. This cursor is going to be able to tell me both the instantaneous and the accumulated readout of every single measurement. What we're going to focus on is the BER. So I'm going to go ahead and zoom in on this section of the graph here, and I'm just going to turn off channels 2 to 4 just to focus on channel 1 here. So you can see we have this cursor, which is telling us every 100 milliseconds what is the real-time and accumulated measurement. So you'll see at around 63.1 seconds, the real-time and instant BR are still at 1E-6. However, if I go to 63.2 seconds, look at that instant BR now. That instant BR is 2 times 10 to the minus 3, which is much, much higher than what a FEC encoding mechanism can recover. So you can see that's a really big error burst happening. If I continue to move my cursor across this graph, you'll see that the instant BR is still around 1E-3, and then the real-time BR is starting to reflect that accumulated bit error, that accumulated error burst with the rest of the data. And then if I go to the end of the error burst after I disabled error insertion, you'll see that instant BR is now back to 1E-6 because I disabled the error insertion, the additional error insertion, and then the real-time BR is at 3E-4, which reflects the whole story. So history navigation is Multilane's way of enabling you guys to be able to have very, very precise tracking of the error behavior of your devices under test. But that is not where the story ends. More than being able to track your error bursts, more than being able to finely tune the equalization being fed in to your module, we need to see how the module will actually perform out there. Well, the module, the switch, the cable, whatever. We need to see how my device is going to perform out there in the field. Because remember now, forward error correction is a mandatory encoding mechanism that needs to be applied to all these PAM4 interconnects. And what we have as Multilane and ThunderBERT is our real hardware-based FEC available on our flagship BERTs. I'm going to go ahead and actually apply that FEC, the signal now. I'm going to apply 400 gig KP4 FEC. So what just happened is you'll see there's only one lock indicator on the receiver side. So that one lock indicator means that I have grouped all 4 electrical channels into a single interleaved, striped, if you will, FEC link, a single 400 gig FEC link with KP4 and Reed-Solomon 544 code words. So now that we remember we had that 1e-6 pre-FEC bit error rate, now we're going to see what happens with the post-FEC story. We've added that FEC. Now the signal is encoded correctly. We're going to go ahead and do the same thing, this time with the FEC measurements being shown on the left-hand side. So I'm going to select time, then I'm going to select, let's say, corrected code words, an instant, and accumulated mode. So accumulated and instant corrected code words. I'm going to take a second to find that right here. And then I'm going to press start for that single link. So now you can see we are correcting a lot of code words because of that high pre-FEC bit error rate. And this is really kind of what you're going to be wanting to track here. How many code words was I able to correct? How many code words was I unable to correct? So when your device under test has that error burst, what you're really seeing is what your system is going to report and how the system responds to that error burst. Is it able to recover those errors? Or is it not able to recover those errors? These are the key questions that you can answer for your DUT with ThunderBERT. So once again, we can choose to filter which measurements we want to take a look at. We can go ahead and apply history navigation. For example, if I apply that same error burst to a FEC link, you'll see that rate of code words that are being corrected shoots up to a very, very high value right over here. And again, I'm zooming in to kind of use my history navigator to see what's going wrong here, or I can go ahead and auto scale and I'm back to the main page. Now, we showed you how we can track corrected and uncorrected code words with our FEC analysis tool, but let's take it one level deeper and talk about SER. So we talked about our FEC implementation here, which is called KP FEC, KP4 FEC to be exact. KP FEC means that in every code word, which is 544 symbols long, up to 15 symbol errors can be corrected. So now I'm going to start that symbol error test to see really what is the margin of my FEC performance. In other words, how many more errors or how many more error bursts can I withstand with this setup before I break that 15 symbol error threshold and start creating uncorrected code words. So now in our histogram, you can see most of my symbol errors, most of my code words only have one symbol error. That's what this tall bar graph means. And that's a good thing. That means we have a lot of operating margin. Now you will see, if I zoom in here, some code words have 2 or 3 symbol errors. And again, that indicates that you have a lot of margin in your system. And as a final touch, what we can do is we can inject some errors in the middle of this SER test. And now you can see that FEC margin has decreased because instead of only having code words with 1, 2, or 3 symbol errors, we have code words with 4, 5, 6, 7, and even 8 symbol errors. And that is an indicator that you're still okay, but you're approaching, the sort of failing edge. So that is really where the story comes full circle, folks. We give our users the ability to finely tune the state of the input and output signals going into and coming out of the DUT. We give a precise, mechanism to sort of track error behavior with our history navigation and our error insertion feature. And finally, we bring it all together to show what the device performance is going to be in real life with our real hardware-based Reed-Solomon encoded and decoded FEC. And that is ThunderBERT in a nutshell, if you will. We are going to have some other demos in which we will be talking about noise injection. We'll be talking about shallow loopback capabilities and other ThunderBERT variants. And we look forward to you guys being able to benefit from all of these virtual demos. So thank you for tuning in. And with that, we will conclude this ThunderBERT demo.